Molarity is the concentration unit that you learned in Chem 1. It stands for moles of solute per liter of solution, and the symbol is a capital M. So we're going to solve this little problem, and let's go ahead and do it down here. So what we want here is we want X moles of sodium chloride in this particular case, because we've got 29.22 grams of sodium chloride per liter of solution. So we've got 1 liter of solution. That's the ratio that we would like to get, moles of sodium chloride per 1 liter of solution. And I'm going to add another decimal place to this molar mass. Shame on me for not putting it in the PowerPoint notes, but here we go. So I've got 29.22 grams of sodium chloride. How do you convert grams to moles? You divide by the molar mass, which you compute off the periodic table. So this is 58.45 grams for every 1 mole of sodium chloride. And then we're going to divide by the total volume of the solution, which is 0.250 liters. You usually don't get this lucky. I was easy on myself. This is just for demonstration purposes. Usually this would be expressed as, say, something like 250 milliliters. You would have to divide that by 1,000 milliliters per liter to get that 0.250 liters of solution, okay? But I went ahead and gave it to us in this one. And if I do that, I wind up with 1 point something like 99956 molar. But since I only have 3 sig figs here in my denominator, I can only have 3 sig figs in my answer. So I'm going to round this to 2.00 molar of sodium chloride. And that's just approximately 2.00 molar. And that would be my answer. So molarity will do you for many things, but in this course we change temperatures of our solutions, and changing temperatures will cause most things to expand to some degree if I heat them up. So liquids usually expand. If I heat them up, they contract if I cool them down. So if we increase the temperature, the molarity of a solution would change. All right, and the same thing's true if we lowered the temperature. So we need a unit of concentration that does not depend on volume, that it doesn't have a component that changes with temperature. So this is molality. I'm so sorry that it sounds so much like molarity, but you need to make the distinction between molarity and molality. Molarity is moles of solute per liter of solution. Molality is moles of solute per kilogram of solvent only. So we get the solute out of the denominator, but it stays in the numerator in mole. It's very similar to molarity, but constant with temperature. So I can raise the temperature, I can lower the temperature. Molality won't change because mass doesn't change with temperature. Usually pretty easy to calculate. You'll need to remember when converting back and forth between molarity, molality, that density relates mass and volume for a substance. So water is 1.00 grams for every 1 milliliter on average. And it will change depending on the temperature on any given day, but you'll need to remember that density relates mass and volume for a substance, and generally speaking, water 1 gram per mil. So here is a problem for us. What is the molality of 5 grams of this compound, diiodomethane, dissolved in 1 liter of ethanol? The density of ethanol is 0.791 grams per milliliter. The key for all of these is to define the units. So molality is what you're solving for. And this is going to be moles of this stuff, CH2I2. We're given grams of the stuff. So we're going to have to convert grams to moles, which we do by dividing by the molar mass. Here's the real issue. We need to have not liters of solution, but kilograms of solvent in the denominator. So we'll need the molar mass of the compound. We've got one carbon, which is 12.01 grams per mole, plus 2 times 1.01 grams per mole. That's the hydrogen, carbon, hydrogen, plus 2 times, and iodine's pretty heavy stuff, 126.90 grams per mole. And when I compute that, I get 267.83 grams per mole for CH2I2. So we can now convert grams to mole. But before we do that, let's take a look at this. Now, this is dissolved in ethanol, so this is our solvent. They didn't give us a solution. They simply gave us a volume of solvent. We just need to convert that to kilograms. So that's going to be X kilograms, and this is the ethanol, and there's 1.00 liters of the stuff. We're going to use density, but the density is in grams per mil, so we need to take our 1 liter of ethanol and convert it to milliliters, and we do that by multiplying times 1,000. That'll cause the liters to cancel. We're now in milliliters, and then we've got 1 milliliter is equal to 0.791 grams, and then there are 1,000 grams in 1 kilogram. Well, that turned out to be pretty silly because we're going to multiply by 1,000, divide by 1,000. 1,000 over 1,000 is just 1, so really we're just multiplying 1 times 0.791 times 1, which gives us 0.791 kilograms of our solvent, which is ethanol. All right, so we've taken care of our kilograms of solvent. Let's get our moles of diiodomethane, CH2I2, and that's simply going to be 5.00 grams divided by this incredible molar mass of 267.83 grams per 1 mole. And to 3 significant figures, that gives me 0.0187 moles. All right, I'm ready to figure out what my molality is. X moles per kilogram. Remember, this is solvent only, not solution. That's the big mistake that people make. I have 0.0187 moles of my solute. I have 0.791 kilograms of my solvent, and that gives me 0.0236 molal. And my molality will not be sensitive to temperature changes because the mass of the solvent will not vary with the temperature changes. All right, so that's how you do a basic molality calculation. Calculate moles of solute, calculate the mass of the solvent in kilograms, and there you go. Okay, divide moles of solute by mass of solvent. Well, there we are. Other units of concentration. The mole fraction is useful, and you'll be using it in this course. And it's just moles of solute divided by the total number of moles. I've listed one here, 0.01 mole fraction is equal to moles of solute divided by moles of solution. Now, mole fraction is a ratio, and it's a ratio that will always be less than 1. Here's what you want. You want X moles, usually of solute. I am going to show you a particular problem where you need to put moles of solvent in the numerator, but we'll get to that later. But normally it's moles of solute divided by total moles. And you have to remember what total moles means. And this is total moles of solution. So what that means is you need the moles of the solute in the numerator, whatever it happens to be, but you also have the sum of the moles of the solute plus the moles of the solvent in the denominator. Now, moles is going to cancel, so there's no units to a mole fraction. It's just a decimal. It's just a ratio of moles of solute normally to total moles. This is total moles down here, total moles. Okay? All right, so we'll work a problem with that. Mass percentage is just the mass of the solute divided by the total mass of the solution. To get it into percent, you just multiply times 100. And so you have the same sort of problem with mass percentage that you do with the mole fraction, in that you need the mass in grams, typically, mass in grams of solute divided by the total mass of the solution. And if it's the total mass of the solution, it's the mass of the solute plus the mass of solvent. And once you get that, you just multiply that times 100 because you want it in percentage. Okay? So it's the same idea with the mole fraction, only you're multiplying by 100 and it's in mass, and it's all in grams. You have to have same units in the numerator and the denominator. Parts per million, if you're a biologist, particularly a wildlife biologist, you're doing water analysis, you're looking at ecosystems, water systems, you're measuring for parts per million in arsenic or mercury or some other toxic substance in the water, you'll use parts per million because those will generally be in a healthy water system. They'll be very dilute solutions. And so you need something that can express a usable value. And so we use parts per million. There are a couple of ways that you can calculate that. Take the mass of the solute, whatever it is, the mass of solute, so it's very similar to mass percentage, but mass percentage is just parts per 100. What we're going to do here, we'll take the total mass, and the total mass is the mass of solute. Now this is likely to be a very small amount, plus the mass of the solvent, but instead of multiplying by 100, we multiply by 1,000,000, and that's to get parts per million. All right? And it's really the same idea as mass percentage, only it's parts, instead of being parts per 100, it's parts per million. All right? You could do the same thing with parts per billion. So there is one other way to do it that is mathematically equivalent, because this is such a dilute solution. And we're usually looking at aqueous solutions. If it's really dilute, if you take X milligrams of your solute and you divide that by kilograms of your solvent, which is really your solvent is most of the solution, because if you're talking parts per million, it's really dilute. This is going to be a very small contribution to the total solution. So milligrams is one milligram is 0.001 grams, and 1 kilogram is 1,000 grams. And so dividing 0.001 grams, which is a milligram, by 1,000 grams, which is 1 kilogram, what you wind up with is parts per million. And I'll show you how that works. You can do the same thing by doing milligrams of solute per liter of a solution, as long as it's a dilute aqueous solution where parts per million is an appropriate measurement. You could even have a more dilute concentration in which you would be dealing with parts per billion, which is just a gram of solute per billion grams of solution. All right, let's do a practice problem. I'll do this problem two ways. So it says the Earth's crust contains approximately 3 parts per million arsenic. What mass of arsenic is present in milligrams in 2 kilograms of soil? So here we go. So what we want is X milligrams of good old arsenic. I think the Borgias used to be very good at poisoning with arsenic, rat poison. All right, so here we have 2 kilograms of soil, 2.0 kilograms, and this is soil. So it's in the numerator, so I want kilograms of soil here. And so 1 kilogram of soil is equal to 1,000 grams of soil. Now, 3 parts per million, what does that actually mean? Well, 3 parts per million is going to be 3.0 grams of arsenic per million grams of soil. So here we go. So 3 parts per million is a ratio of 3 grams of arsenic per million grams of soil. So here we go. So I have 10 to the 6, that's a million grams of soil. This is going to enable me to cancel soil. This is going to give me 3.0 grams of arsenic. And then 1 gram of arsenic is equal to 1,000 milligrams. So let's take it out. Take a look. Kilograms of soil cancel, grams of soil cancel, grams of arsenic cancel, and that leaves me with milligrams of arsenic. And when I work that problem out, I wind up with 6 milligrams of arsenic. So there's an easier way to do that using the milligram to kilogram ratio. We still are looking for milligrams of arsenic. We've still got 2.0 kilograms of soil here. And so we're going to have 1 kilogram of soil. And since it's 3 parts per million, what we are saying is that 3 parts per million is 3 milligrams of arsenic per 1 kilogram of soil. And so this is going to be 3.0 milligrams of arsenic. And that seems a little bit simpler. Kilograms of soil cancel, so that's just 2 times 3, or 6.0 milligrams of arsenic. So this is a very handy way to work this type of problem. I would remember the ratio of milligrams to kilograms of your solvent when you're doing parts per million. Units of concentration, helpful hints. The mass of a solution is the sum of the masses of both solute and solvent. Don't forget that. The density is a conversion factor between mass and volume. As long as we're working with solids and liquids, the mass will generally be in grams, the volume will be in milliliters, and so density will be expressed as grams per 1 milliliter. And so since you have mass, grams, and volume, milliliters, you can use it as a conversion factor. You can use it if you're going to grams from volume, you can have grams in the numerator and milliliters in the denominator. If you're going from mass to volume, you would just invert this. And we'll show you how to do that both ways. All right. So how many grams of glucose must be dissolved in 563 grams of ethanol to prepare a 2.40 times 10 to the minus 2 molal solution? So the key to this is to get your terms straight. This is molality, and molality, if you remember, sounds like molarity, but it's molality, and that's going to be moles of solute per kilogram of solvent. Kilogram of solvent. Okay, so, and that's, when we finish that out, that'll be moles of solute per 1 kilogram of solvent. So we need moles, and that is right here in this concentration. This is telling us how many moles of solute there are in 1 kilogram of solvent. I'm going to go ahead and use decimals here. This is going to be 0. And all we're doing is moving the decimal place 2 places to the left. So that's going to be 0.240 moles of glucose, the C6H12O6, per 1 kilogram of ethanol. So this is kilograms of eth, and this is moles of C6H12O6. Okay, so this term right here is that concentration, and that's what we're going to use to figure out how many grams of glucose we need to make this concentration of solution. X grams of C6H12O6. We're going to start out with the grams of ethanol. I think you might be able to see where we're going. So 563 grams of ethanol. I'm just going to say, well, okay, ethanol. We need to convert it to kilograms. So there are 1,000 grams of ethanol, eth, per 1 kilogram of eth. And I'm just putting that up there so I don't forget what I'm talking about here. All right. Now, my concentration is this. It says in every 1 kilogram of eth, I've got 0.0240 moles of C6H12O6. And then finally, I'm going to convert moles to grams. 1 mole of C6H12O6 is, I think, 180.15 grams. I might be off by a decimal, but I think that'll work out. So we've got grams of ethanol over grams of ethanol cancel. Kilograms of ethanol over kilograms of ethanol cancel. Moles of glucose over moles of glucose canceling. It's late. I'm tired. And so we've got, when we work all that out, 563 times 1 divided by 1,000 times 0.0240 divided by 1 times 180.15. Okay, and that gives me 2.43 grams to 3 sig figs. 2.43 grams of C6H12O6. You can check that very easily by simply going back and computing the concentration, and you've got everything that you need to do it. You've got your 2.43 grams of glucose. You can divide by the molar mass of glucose, which is in grams per mole, and then you can divide by your point. If we divide 563 grams of ethanol by 1,000, we get 0.563 kilograms of eth. Okay, so let's just make sure we're all on the right page. Divided by 180.15, divided by 0.563, and voila, I get 0.0240 molal. So that gives me my concentration back, 0.0240, lowercase m, that's molality. So we're good.